Hi, my name is Hamza Hassan, and in this video I'll be demonstrating my revised final year project. So now the project itself moves beyond the original static content delivery approach, now that I've implemented a dynamic DynamoDB backed product catalog API, which I'll show you further on in this demonstration. However, now the testing includes functional API testing, cold start versus warm start, geographic latency testing in terms of globally and also locally in the UK, CloudFront cache behavior analysis, monitoring and observability validation between both architectures, cost analysis between both architectures, and lastly, concurrent load testing. Now that I've extended it and developed two custom K6 workload scripts for both architectures, which I'll show you further on in this demonstration. However, firstly, I would like to show you the new updated design of both. So firstly, started with the regional design. As you can see, firstly, a user or client would send a HTTP request to Amazon API Gateway. Then the API Gateway would then forward the request to the regional AWS Lambda function, which is deployed in EUS2. Then this function would read the query parameters provided from the user, then would access the DynamoDB product table and filter the results and the records, and would return a structured JSON response. So I've also used AWS CloudWatch to actually log and collect metrics from this specific regional AWS Lambda. So both regional AWS Lambda and DynamoDB, both of them being deployed in the exact same region of EUS2. Now to show you the edge assisted architecture, which is an extension of the previous centralized architecture. As you can see, however, firstly, the client will send a HTTP request to AWS CloudFront first. And the Lambda Edge, which is attached to the CloudFront's viewer request event, this is where it would add the custom headers to mark that the request has passed through the edge assisted path. So CloudFront would then forward the request to the same regional backend. So the decision behind the design is that the DynamoDB access and product filtering still happen in the regional Lambda backend. However, the Lambda Edge does not directly query the DynamoDB. So I've kept the Lambda Edge lightweight, so both architectures use the same data set and they would use the same filtering logic and the same response structure. So now the comparison is much more clearer and fairer because the main difference is now the infrastructure path rather than the different application logic. Now to show you this through the AWS console, firstly, I can start with the DynamoDB. So this would be the products table. And as you can see, each item contains fields such as the product ID, the category, the name, the price, the region, and the stock, which are all predefined. So the regions being Australia for AU, Denmark for DE, SG for being Singapore, US for United States, and UK for being United Kingdom. And the categories being console, laptop, tablet, and phone. So the key idea is that now this shared table is important because both architectures are tested against the same backend data, meaning any performance differences cannot be explained by different data sets. Now to show you API Gateway and to show you the configuration. So this would be the endpoint URL. And as you can see, if I was to show you the regional Lambda, here is the integration with the regional Lambda. So this would be the trigger. It would trigger the regional Lambda and expose it as a public HTTP endpoint. Just to show you also the Lambda Edge, which is deployed in EU West 2, which is also attached to the viewer request header, which I can also show you in the CloudFront distribution. So here is the CloudFront distribution. Here is the domain. And this is the public endpoint. So for the Lambda Edge path. So just to show you, the Lambda Edge function is attached to the CloudFront's viewer request event, basically. So now just to show you a live demo before I go into detail of the code and the architecture and further. Firstly, we'll test and validate the system. or both systems. So firstly, we'll check the regional Lambda endpoint, so providing the region of the United Kingdom and the category of laptop. So it should provide a response in JSON. And as you can see here, it shows the filters, so the region being United Kingdom and category being laptop, and the count, which shows any matching results, and also lastly the results array, which contains all the returned records. So this confirms that the regional Lambda is retrieving and filtering the product data from DynamoDB directly. So now, for example, I could show another region such as US, so it shows correctly. Now, just to show you the CloudFront endpoint, and we can test the exact same region, exact same category. However, through the CloudFront endpoint, it should return the exact same JSON, which it does. So it shows the same filters, the same products. So this confirms that also the CloudFront and Lambda Edge path is forwarding the request correctly to the backend. Keep an idea that this is the first time that I've tested these URLs today. So now, just to show you invalid input and how the systems handle it. So we'll test firstly the regional system. So firstly, we'll test the regional system, and we'll change the region to, for example, ZZ, which, as you can see in the data set, there's no region set as ZZ. So as you can see here, it provides the count as 0. And also there's an empty results array. So there's no crashes, there's no server error. And also, for example, if I was to change this back to United Kingdom and the category to monitor, it would show the count 0 and empty results array as well. Now, just to show you the same system, however, now with the CloudFront endpoint and how it handles it, we'll test ZZ. Again, it shows the count is 0 and the empty results array. Now, for us to get it, now we'll get into the code of both functions. We can start firstly with the regional Lambda function. So this is the main logic for the product catalog application. So firstly, at the top, this is where I import the DynamoDB client and also the document client from the AWS SDK. So this allows the Lambda function to connect to DynamoDB and also work with records with the standard JavaScript objects. So the next two lines is where I create the DynamoDB connection and specify the AWS region. So in this case, the function connects to DynamoDB resources, which are hosted in EUS2. And just to show you, the DynamoDB is hosted in EUS2 also. So now in the main handler, in the main function, as you can see, the first key thing is async. So usually Lambda functions often perform operations that take time to complete, such as querying a database. So by having this handler asynchronous, I can use later on the await keyword to pause the execution until DynamoDB returns the response. However, the function firstly receives an event from the API gateway. This contains the query parameters supplied by the user or from the user. Then the code would then extract these parameters and normalizes. So the two being region and category. So the region values are converted to uppercase because the DynamoDB dataset stores the region codes as capitals. So if I was to show you here, they're all capitals. And also the categories are converted to lowercase because to match the data stored in the dataset as well, basically. So next, the function performs a DynamoDB scan against the products table. So essentially, the function waits for DynamoDB to return all of the product records before continuing. And then basically, the returned products are then stored in an array. So, and then filtered also according to the parameters which are provided by the users. So based on the region provided and also the category provided, basically. So if a region is provided, then only the matching regions are given basically, or returned. And if a category is provided, then only the matching categories are provided as well, returned. However, if both are provided, then both filters are applied. So then once the filtering is completed, then the function will return a JSON response containing the architecture name, basically the filters or the applied filters, the product count, the results, and the timestamp basically. So the response is then returned to the API gateway using a standard 200 HTTP response. And finally, there is a catch error for error handling. So any unexpected errors are written to CloudWatch logs in a structured HTTP response basically. So one decision behind the design worth mentioning is the DynamoDB scan. So this I've done rather than the query. This is because this project itself uses a small data set, as you can see. So scan would be efficient for a small data set compared to, for example, in a production environment, the table could be redesigned or use query operations for better, for example, scalability or efficiency, etc. Now to show you the Lambda Edge code. So intentionally, the Lambda Edge code is much smaller than the regional function code, the regional Lambda code, because it does not perform any database operations or any sort of logic. So firstly, the handler, just like the regional Lambda, uses async. So it's asynchronous because it processes CloudFront requests as part of a request pipeline. So the first thing is that it would extract the incoming CloudFront requests from the event object, basically. So this gives the function access to HTTP request before it reaches the origin infrastructure. Then the function would then add two custom headers. So the first header simply records that the request was processed by Lambda Edge. Then the second records the architectural path that the request follows, basically through CloudFront, through the Lambda Edge API gateway, Lambda, DynamoDB basically. So after the headers have been added, then the function immediately returns the modified request basically. So at this point, the Lambda Edge function has completed. So it's finished executing. So CloudFront would then later decide whether it would serve a cached response directly from the edge location, or whether the request should be forwarded to the regional backend, the regional Lambda backend. So the key design decision in this project was keeping all the product processing logic inside of the regional Lambda instead of the Lambda Edge. And the Lambda Edge does not directly query the DynamoDB or filter the products or generate responses. So this ensures that both architectures remain functionally identical, and as a result, any performance differences would be due to like CloudFront caching and also edge processing rather than application logic. Now, in terms of testing wise, so the first thing that was done was in terms of the functional API validation. So before any performance tested, I had to validate that both architectures return the correct results. So I've tested the region filtering, also the category filtering, also both. I've also tested the non-filtering. So as you saw earlier, the non-filtering to see how it handles invalid regions, and also, for example, invalid categories. So this step was necessary. So I had to do this step before moving on to any sort of performance results or performance analysis, because both systems have to be functional and equivalent, basically. Sorry, not equivalent, but functional. So the first thing that was tested was cold start versus warm start. So the cold start testing was firstly tested for the regional Lambda, which was much more easier to observe through the CloudWatch logs compared to the Lambda Edge. So essentially, this is the delay that's caused when the Lambda needs to initialize a new execution environment, basically. So for the regional Lambda, how I tested the cold start is that I introduced 10-minute idle periods. So I would test will send a request through Postman, a GET request, and then wait 10 minutes and then send another request after 10 minutes. So showing the results for the cold starts, as you can see here, I'm basically for the cold starts for the regional Lambda, I've sent 4 requests. So CloudWatch confirmed also that the init values, the init duration values was around 350 to around 376 basically. So milliseconds. So this confirms the elevated response time came from the runtime initialization rather than any slow application logic. And also the Postman total was higher than the CloudWatch because it had to include aspects such as the API gateway routing, TLS negotiation, and also any network transmission. So also for the regional Lambda, for the warm start testing, I sent it straight after the cold start testing. So it was 10 iterations. As you can see, I've done an average excluding the initial invocation because essentially the first invocation as you can see here in the warm start was much higher than the other requests. So this could be due to additional overhead such as network variability and API processing, and also just internal AWS scheduling. However, here is the results for the warm starts. As you can see, it dropped between 426 milliseconds to 726 milliseconds. So it shows the improvements in latency in terms of warm start versus cold start. And lastly, for example, the Lambda Edge was mainly tested through Postman. So the cold start analysis was much more difficult internally because the logs are more distributed across CloudWatch regions, depending on which edge location handled the request basically. So I mainly relied on the Postman timing and also the Lambda Edge cold start evaluation basically. So I mainly relied on Postman in terms of the response time and also looked at time to first byte, etc. So now in terms of cache behavior. So in terms of the cache behavior and how I analyzed it, the first thing I tested is the cache request evaluation. So this was to see and send constant requests to this specific endpoint, the Lambda Edge endpoint, and to measure the average latency, the adjusted average latency, excluding the first request, which was a cache miss, and then to show the minimum latency and maximum latency. And also I've done a test to try and see the cache bypass. So essentially I've done repeated requests to the CloudFront endpoint in terms of to see in the response headers to confirm if how long it takes until after 20 iterations that the responses are served from the cache. So essentially I found that even after that, this revealed that the CloudFront cache policy didn't include the cache bus parameter in the cache key. So changing it did not invalidate it basically. So yeah, so now moving on to the region in terms of the latency. First of all, I tested the UK baseline in terms of the regional Lambda endpoint, which I sent 20 iterations to the regional Lambda. And then lastly, I captured the average latency from the UK baseline and the average latency excluding the first invocation, which is due to a cold start, and then the minimum latency and maximum latency. Then I've done the same thing for the regional edge endpoint, 20 iterations to get a more collective result for the UK baseline, and then done the exact same thing, extracted it, and that's my baseline for the UK baseline. Then lastly, I compared this baseline against United States, Singapore, Australia, and then compared these results. And as you can see in this graph, gradually, as you move away from the UK, the average latency for the regional Lambda and the Lambda Edge gradually increased, showing that as the distance increases, the latency would gradually increase as well. And also I compared in terms of locally, in terms of the UK, in terms of Manchester and Edinburgh, and I was able to extract concise results. However, the key test that was done was the concurrent load testing. So instead of previously I done sequential load testing through Postman, it didn't really represent real world applications and how users interact with applications. So firstly, I would like to show you both scripts. So both scripts. So firstly, showing the regional. So firstly, I imported the HTTP module so that the K6 can send actual HTTP requests. Then also I imported the sleep so that it can pause between requests and check to validate responses. And then here in stages, this is where I defined the load profile. So ramping up from 10 virtual users to 50 to 100. And this would be over a duration of 90 seconds. And then lastly, setting the target to 0 after 10 seconds. And also the thresholds were set. So the threshold of the 95% of requests must be completed under 5,000 milliseconds, which is 5 seconds. And also the HTTP rec fail. This is basically to set the threshold that means basically only 10% of requests can actually fail. And then this function here, this is what every virtual user would run repeatedly throughout the test. Basically, this is the function set. So the HTTP get, this is the get request to the regional Lambda endpoint, and then it would validate the response and return the HTTP 200, and then lastly will sleep. Now, this is for the regional K6 script, and also the Edge script is the exact same structure. However, it's just targeting a completely different endpoint, so the CloudFront endpoint instead. So this keeps the test conditions consistent between both architectures. However, the important point is that these scripts test concurrent traffic, so not sequential anymore. So it's multiple virtual users are sending the requests, so it's genuine stress testing basically. Now, just to show you it live. So for example, as also you can see that I'm testing the same exact URL. So the region US category laptop and also the region US category laptop. So we can test it. So first we'll test the regional test basically. So the regional endpoint. So as you can see, now it's ramping up the virtual users and sending the concurrent requests to the regional API endpoint. So while it's running, K6 is recording the request duration and also the throughput, the failed request rate, and also the percentile latency values in real time. So as soon as the results shows, I'll show you. So for example, I can stop it even. So we can see the threshold. So this is the thresholds and also the total results. So the amount of requests, the amount that was succeeded was 100. The checks that were failed, which was 0 that were failed, and the status being 200. So basically, of course, in the real test, in the real testing, basically I left it running for a while to the point, which I should show you the results here. To the point it was a total of 3,613 requests to the regional Lambda and also 3,506 requests sent to the Lambda Edge. So it was much more requests sent. However, now I can show you also the Edge test. Sorry. Edge test.js. Also, we will stop it after like 2 seconds. It should show us the results. However, I left it running. And then again, it shows the thresholds. It shows the total results. It shows the response. And yeah, so that's for concurrent testing. And basically, looking at the results that I've got, is that I found that the regional Lambda achieved a lower average latency of 53 milliseconds, but the Lambda Edge retrieved a much lower median latency of 26 milliseconds, and also lower P90 of 94, lower P95, and also a lower failure rate. So this is the key point, the failure rate. So essentially, there's no sort of simple win between both of them for the concurrent load testing. However, I can say that the regional Lambda performed better on average, but the Lambda Edge showed stronger typical response behavior, basically, and a better failure rate, and more resilience towards the concurrent load. So the Lambda Edge maximum latency was 5,350 milliseconds, whereas the regional Lambda was 1,340. So this could be likely caused by cold start or even edge routing events. So this is during basically peak concurrency, basically. So just to show you also the CloudWatch monitoring. So basically we've just sent requests now. So mainly CloudWatch was used for the regional Lambda. So logs shows the invocation activity, etc. However, for the Lambda Edge, the observability was much more complex. So just to show you, in the specific region of EU-West2, which is the region where the regional Lambda is located. Also, we can show the most recent logs. As you can see, here is the bill duration. So here's the memory size, the etc. This is all the details. So from start to end. So this is exactly where I've extracted a lot of the results actually from, such as the init duration, etc. So in terms of monitoring wise, between both, it was much easier to monitor the regional setup rather than the Lambda Edge setup. However, I was able to use, it was much more concrete evidence for the regional Lambda based on that. So in terms of the cost part of it, in terms of the analysis between both, so in terms of the regional architecture, it cost around £2.50, and during an experimental period covering the API gateway and Lambda execution, the edge assisted architecture cost around £4.95. So it's roughly double. So that's mainly due to the CloudFront distribution and also the Lambda Edge execution costs. However, the total experimental cost was £7.45. However, this is an important trade-off because Lambda Edge can improve performance for distributed workloads, but it adds more cost and complexity in terms of complexity overall. However, the main limitations that I've had for this project as a whole is that the data set is quite small and read heavy. And also in terms of the geographic testing, I use Norton VPN. So the fact that the VPN endpoints were used rather than the real distributed clients, and also both architectures still depended on the EU-West2 for DynamoDB access, because the DynamoDB was deployed in EU-West2. However, future work, I could extend and address this through multi-region DynamoDB replication, maybe larger data sets, maybe write-heavy workloads, and generally just distributed tested clients more. However, just to summarize, this project as a whole, this revised project, however, now implements a dynamic DynamoDB-backed product catalog API and now compares two functional equivalent serverless architectures through functional validation, cost analysis, warm start analysis, geographic latency testing, cache behavior evaluation, CloudWatch monitoring, cost analysis, and lastly, K6 concurrent load testing. So the main conclusion is that Lambda Edge can improve performance for geographically distributed and cache-friendly workloads, but it's not automatically better in every scenario. And the regional Lambda is much more simpler, cheaper, and more effective for localized workloads. The best architecture, I think, I believe depends on the user location, the cache behavior, also the workload type, the performance requirements, and observability needs and costs. That's what I've discovered from this project. However, this has been my demonstration. Thank you very much for listening.